Hello, everyone. It's Katerina Pekova, the STRV Community Manager. Again, it's really nice to see such a great show up either here on Zoom or on our YouTube stream. I would like to welcome you all here at our fourth Backend online event in 2021. I hope that this talk will go without any major technical issues and everything will run just smoothly. So firstly, let me cover some basic rules so you can experience this talk as lifelike as possible. You have many possibilities how you can interact with the speaker or with another attendees. So first option is that you can raise your hand. That would be our priority. So every time anyone will raise their hand, we will unmute you and you can ask the speaker directly. Also, you can post your question into Q&A section. We will get to those when it's question time. And also you can write us in the chat. Just be aware to address your message always to the right person or the group of people. Okay, so that's basically it. And I would like to introduce our speaker, Juan Scolari, our backend developer at STRV, and along with him, Michal Kačko, who is backend lead at STRV and whom I would like to give a word right now. Thank you and enjoy.
Hi, everyone. As was said, I'm Michael, the backend lead at STRV, and I would like to welcome you here on this backend online talk as well. Before we will start with the topic and the presentation, I would like to do a little bit of promotion, and that is that we are currently hiring. We are hiring for many positions, but I would like to highlight the backend developer one right now. As you know, our primary tech stack is Node.js. We are open to all seniority levels of engineers, and as you may know, we are working on many cool startups or running companies, mostly in the US, but also everywhere in the world. So now let's go to the topic. At STRV, we work on many different types of projects, mostly like typical startup apps or websites or even some company systems. But from time to time, we work also on some exciting games, which many times have the multiplayer aspect. And Juan Scolari, our today presenter, is working on the backend side of one of them. Even though this topic or presentation is not going to be about this specific project he is working on, he definitely has a lot of experience from a field working on a multiplayer game with a high concurrency. And if you are interested in the project he's working on, it's called Life Penalty. It's available on App Store and I believe Google Play. And it's quite unique game. And when I say unique, I really mean it's unique game. So definitely check it out. And now, without further ado, Juan Scolari and how to create a scalable multiplayer games on the clouds. Thank you.
So thank you, Michal, and thank you all of you for joining our meeting. So we'll be discussing some topics about game stuff, like server stuff, but maybe not on the application side, but more on servers and the cloud on how to scalate them. So as Michal was saying, I'm working on Live Penalty, which is a really cool project. You should check it out. We are using live streaming. We are using video on demand streaming and many other things. And on the way, I learned a lot of lessons. So I would like to tell you some of these lessons I learned on the way. I've been working in IT for some years, but it was the first big project I've been working on for gaming. And yeah, without further ado, let's start with the talk. So how to create scalable multiplayer games on the cloud. Yeah, I'm Juan Scolari. There you can see me working hard on some solutions. I was thinking, if you want to enjoy this talk better, you can also have some beer. You'll definitely enjoy it. So as Michal was saying, I'm a backend engineer working here at the STRV. I'm also an AWS solutions architect. So if you see that I talk about AWS, you can replace it with any other major cloud provider like Azure or Google Cloud. And my favorite game, by the way, is Tetris. So If you want to join, like, what's yours? So I'm more a retro game fan. I'm 33 years old, so I grew up with the NES console, so pretty familiar with those type of games. But now I'm working on these multiplayer things, and they are quite challenging. By the way, I'm from Argentina. Now I'm here at our office in Prague. And if you want to follow me on Twitter, you can do it at Juan Scolari. And let's begin with the talk. So, multiplayer games, they have many challenges. It's different than developing normal applications. They share some points, but it's not the same thing. So some of the things in which they differ from any application that you usually develop is that you need low latency. You know, when you're playing a game and you're experiencing some lag, man, it's awful. Some people like start with raging and rage quitting, and you have to be special attention to that. So what it's also different from these game applications or these games from normal applications is that you often have real-time updates. So
Juan,
imagine you're...
sorry, you are not sharing screen if you wanted
Oh,
to.
thank you.
No worries.
Oh, so now you can see my awesome profile picture, and you know what I'm talking about. Good. So thanks, Michal. So there you can see me. And I was talking about multiplayer game challenges. So basically low latency, real-time updates you'll find in most games, which you're playing against someone else at the same time. There's also some specific thing that you have to think about. It's that it's very write heavy. So maybe in some applications like Instagram, Facebook, or whatever, you send a picture, you post something, and you expect to have a lot of reaction, likes and dislikes and everything, comments, but it's usually people that seeing that and going through the feed. And with games, the thing is that you're always pushing some updates to the server. So it's important to have some databases that support that and some patterns. So that's basically what we be talking about, and some specific features like matchmaking, leaderboards, achievements, and in-game purchases. So let's start with the first part of the presentation, which is servers. So we'll talk about two types of servers, like normal API servers and game servers specifically, but let's start with the API servers. So first of all, these ones are the ones that will process non-real-time data, and we'll see what we are talking about and why. Because it's easy to scale them horizontally, so that means that you can add more servers, and it's really easy. So you scale them up the same way that you do with normal servers for your usual applications. And we'll see like some basic design of this. So you have all of your users, and you have your cloud servers, and you'll communicate with your servers through a load balancer. So a load balancer, you know, it's like a kind of proxy that you can make your users go to it, and it will select some of your servers that you have. And in case you have a lot of traffic, it can have like an auto scaling, and you can say that whenever it surpasses 80% of your CPU, you can add more servers. So it's really easy to scale servers with this. If you're using some managed platform like Heroku or AWS Beanstalk, you'll see that this is done directly by the platform. You don't have to worry about it. But it's a really, really common pattern, and we'll see how we'll use this on games, like on different APIs. So some general use cases that you can use these API servers are basic stuff, like you always do, like login, sign up, sessions, profile. Maybe you have some trophies or achievements. You have your friend list. You have in-game purchases. So you're buying something with your phone. You have to request it to Apple or Google, and you'll have a callback, and you'll apply like the same concepts that you apply for any normal application in this. And you can also develop some types of different games. So basically turn-based games. So games that are not real time, that don't depend on the two people or many people like being at the same time playing. So you are not expecting real-time updates. So basically you can communicate with an API, and that's maybe the first approach you should try if you can, because it's easy and it's easier than the other approach. But depends on your use case if you're developing a real-time game, or it's like one that you can just send an API and let the other person do what they want like later. So basically, yeah, turn-based and non-real-time games. And we'll see some examples here. So I'm not sure if you know which game is this. You can guess. But you can do this, all of these achievements, stuff, profiles, statistics, careers, all of this stuff. You don't need any type of different approach like you'll do with a normal server. You can also do, you can also buy some stuff. You can retrieve some data, and you'll find that a lot of times you have to develop these endpoints, these kind of things that are not game servers. They are like normal stuff, but sometimes you'll have a lot of things on your menus. You'll interact with your players in different ways than the in-game experience. So you'll have to do them, do some quests, maybe train your character. Maybe you want to buy some more stuff and you want to have some revenue. So you probably want them to purchase some things, and maybe there's a cooldown and all of these kind of things. Maybe you don't need real-time updates. So you can implement it this way. And maybe you have some game like this that you perform some actions and you'll end your turn, and maybe you leave and you're expecting someone else to take some action, but maybe not in real time. There are some games like this, especially mobile games, that don't require you to be at the same time that other players, but you can send your action, what you'll be doing, and the game expects that not real time, so that you get back in some hours and maybe you collect some stuff and you can farm your characters or your city. So this is like one use case. And with this, you can think on like normal approaches with normal APIs, and you can develop your own game with this. So I'll make some tips and suggestions for you, like implement APIs for every part of your game that doesn't need real-time updates. So you can develop your whole game with normal APIs, or you can like add special features like the ones we saw for any part that you don't need real-time updates. So as we said, it's really easy to scale horizontally to add more servers. Another point like I like to mention, you can use middle-sized server instances. You don't need like really big ones. They are cheaper, and you can use like general web instances that you'll use for any web application. Also, it's easy to scale them horizontally, as we were using these load balancers. And lastly, we were talking about load balancers, and some very important thing that I learned was that you have to pre-warm your load balancers if you're expecting spikes. So what does it mean? Imagine that you have an important event. So you're expecting a lot of people. You have some special guest on your server. You're expecting like some special thing. You have a live event. You have an international event. Maybe it's now we have the Euro Cup and it's FIFA times, and more people join the game because it's about football, or maybe you're expecting more people for some reason, or maybe you send a notification and it happens that a lot of people got engaged, and you get a lot of traffic like in a spike. The thing is that with load balancers, they are really bad at scaling really quickly. So we said that we can add some more servers, so whenever the CPU surpasses a certain amount. But in reality, in practice, load balancers don't scale that fast, so it's not instant. It's about like 2 times every 5 minutes in AWS, for example, and in other service providers, it's maybe similar. So what you have to do, this kind of sounds ridiculous, but you may need to contact support if you know that you have this spike of traffic, or you have to do it manually. So what the load balancer expects is that the traffic grows, but step by step, like maybe you have 1,000 concurrent users, and you can jump to 1,500, and then to 2,000, and then to 3. But you cannot jump from 1 to 10,000. Maybe you can jump from 1 user to 10 users. It will be fine. But you cannot do these big jumps. The load balancer will suffer. So try to contact support if you know, or do it manually, or do it in a different approach. So that's it about API servers. I hope that you know which character is the one on the bottom right. It's one of my favorite games as well. And now we'll jump to the second type of servers that I like to talk about. So these are game servers. So these are the ones that everyone's was probably expecting that I was gonna talk about. And these game servers, you can think of them that are dedicated servers. Well, we'll talk about this, that will process all the game logic in a stateful way. Whoa. Again, so they are servers. You can imagine that there's only one server, and you'll have all the game logic there, and it will retain the state of the game. So imagine like you're in an open world, maybe World of Warcraft or some open world game, and you have to process like everything that all of your players are doing. So if one character is running, the other is jumping, the other is doing some other stuff, you'll have to work on some collisions, you'll have to work on a lot of stuff at the same time. And the game state can be like really intricate, like really tough to store somewhere. So a lot of times you'll use this type of servers that will hold all of the logic, and they are really, really useful for real-time games because you want things to be fast and to have low latency. And how do they achieve this? Is usually you connect your application, your mobile game, your iPhone, your computer to one of these servers, and you try to, most of the times, or it's a good approach, to try to connect directly to the server. So no middleman, no proxy, no load balancer. So this is one approach, and what you'll gain is that you don't have latency in the middle. So if you can connect directly to the server via usually WebSockets or any kind of sockets, the latency and the cost of the request, the network cost will be reduced. And also if you use sockets, you won't need another type of layer on your network connection. So whenever you connect to this server, you have very fast responses. And with WebSockets, you send a message and it goes directly to the server. The server can process it. And the good thing is that the server can also send an answer to the applications and the mobile devices or your computer. So it's bidirectional. It's different than you usually do in your applications, that you expect the application itself, the device, to send some data and the server will respond. So now you can, let's say that you were shot and unfortunately you were killed. So the server will let you know very quickly. And the quickest way is via a message through these WebSockets or this kind of sockets. And whenever someone closes the connection, it's notified to everyone else as well. And the good things about game servers, as we were saying, is that they reduce client-server latency, so it's really, really quick. Players connect via UDP, which is some protocol, TCP or WebSockets. Server and clients can initiate messages. This is really, really important because in games, you have one of the most important features in real-time games is that server can send messages to other players. Can be difficult to scale. That's not so good part because it's stateful. So stateful and especially with sockets means that one server is holding all the logic. And what happens is that imagine you have like a very, very, very small server instance. And you'll want a lot of people to connect to it. Why very small? Because you want it to be cheap. So you want everyone to connect there. But the thing is that it won't be enough. You'll need more servers or some way to scale. The problem is that with WebSockets, you connect directly to the server. And if you connect directly to the server and you add more servers, you cannot let those people reconnect to some other servers. So once you start the connection to some WebSocket, you'll hold it as long as you can. And the game logic, as we were saying, was hold all in that server. So imagine if you start some other server, how will you communicate all of this state that you have? So all of this open world that you have. So if you're using some game server, like in this scenario, you won't be able to do that. So there are some tactics to bypass this, but you can now have a picture of why it is difficult. So we'll see some use cases for these game servers, as we were saying. Any real-time player action that you can think of: move, attack, shoot, jump, dance, whatever, or everything your character can do. But then you can think of other type of features like real-time game leaderboards. Imagine you're playing like CS:GO and your team is winning. How do you know that that you are winning? Because you have some leaderboards, but they are not like the war leaderboards that the normal leaderboards you see on a web page. They are inside the game and they are related to the game. So you can also use it for game invites because you want your friend to be notified instantly. Chat as well because it's you want everyone to be notified in the spot about anything. And types of games, any modern real-time game you can think of that are really popular now: battle royale shooters, multiplayer, massive multiplayer games, any type of real games. So you can think about Fortnite. You'll see that there are a bunch of stuff there. So you probably need some game server for that. You can also think about chat in any applications, and even like real simple games like this benefit from these game servers. But maybe for these simple use cases for chat, maybe you can think of some other approach that we will see later. Or even so for some like board games like chess, you may think that you'll implement it with some API because it's like move the king one step like above, and that's it. But you see there are some timers there, and like some people in chess, they play with these timers, and you'll want to make your move fast so because time's running down, and whenever it reaches 0, you lose. So you can make an API call and expect to receive the answer really, really quickly. So you usually use these game servers with WebSockets. Also, the state can be challenging. Maybe not for this one. We talk about the state, so it means like imagine the state means every piece in every position, you have to know where it is. If you're doing some game, chess game like this, you'll have to store it somewhere. If you store it in a database, you'll have to retrieve it. Maybe for chess, it's okay. And that point, you can see it. Maybe you can even remember where all the pieces are. But in some game like Fortnite, as we saw, like maybe you cannot store everything and retrieve everything you need to calculate things. So this use cases, game server will be good. So some tips and suggestions for this. As we said, use dedicated servers whenever you need real-time data. Use API servers on the all other cases because you can scale horizontally, and as we were saying, it's easier and it's more common practice. You'll find people, more people that know how to do that. So that's also like some good pattern. If you're building a team, you don't need everyone with a lot of experience in gaming, like for your backend. It will be awesome if you have everyone know about everything. But if you have someone with good experience in normal API development, you can do a lot of stuff in your game with that. So next tip is use large computer instances for your servers. So for API, we said middle size, but with this server for games, you'll want some bigger ones because they have more compute power. They usually have more network traffic inbound and outbound. So that means that you can receive and you can send more traffic. And you have to think that you usually use one big server. Depends on your use case and how your games are structured. So maybe you have a two-player game like chess, but maybe you have a multiplayer game with a lot of people, like 10,000 people playing all at the same time. That would be tough, but you'll need a really big server so you can benefit from it. And especially for Socket, as we were saying, because you'll have to communicate with all of these people, and you won't like to block your server or run into RAM issues. So go for pay and go for a good one. And finally, as we were saying, connect directly to the server so you can reduce latency. Try to avoid load balancers or any type of proxies. You're gonna do that always, but if you can, it's usually some good practice. But what if you want to scale your games horizontally, as we were doing with the API servers, and you have like all of these thousands of players that are playing your game? Or maybe you're playing like in an open space world with a lot of players, and you're playing on the same world. So that can be like complicated. So like a usual approach to this is like you can have a load balancer maybe, but it's different. So because we said that you are only connected to one server, so why is that? And the answer is on the right side. It's the pub sub server, so that's publisher subscriber. And what does it mean? It means that a third party, in this case, is gonna hold all the game logic. So whenever you have some changes, that third party will notify all the other servers. And those other servers will connect through WebSocket and will notify the clients. And if you need to scale to more servers, you can do it because the game logic won't run only on one server, but you can use more of them. So this is a good approach, but maybe you can do this if you have like a very concurrent game with a lot of players. As always, with any kind of architecture, start easy. And then as you find more issues, or if you're expecting some different, like a lot of amount of players to be joining, or you have some metrics that support it, go on to the next step, because things can get really complicated from this is like a very basic pattern, but it can run crazy. So again, start with one WebSocket server and then scale it like with different architecture like these ones. By the way, on the right side, you probably were thinking what's this pub sub server. You can think of some database like Redis. So Redis supports this pattern. So whenever you store something in Redis, you can listen to those changes, and it can communicate with your servers, and you can send it back to the users. You can use some message brokers like Apache Kafka or RabbitMQ, And there are probably more that support this type of pattern. It's a common pattern, and it's one way of decoupling the application, and so that you don't have all your logic on your servers. So give it a chance if you expect a lot of traffic and if you have like really big words. And that's it about these game servers. Well, we'll see some other approach. And it's serverless games. So you're probably familiar with serverless. It's basically no servers, but yeah, they are actually servers, but you don't manage them. You can think it as a replacement of your normal API servers, but in this case, we'll see a replacement of these game servers. So these game servers, we said that you connect via a WebSocket. So your players, instead of connecting to the game server, they will connect to in this case, it's AWS API Gateway. So it's a tool that AWS provides for serverless. And you can think that it's like an API layer. So it shows you like some API like connect/connect. And your mobile devices will connect there, and it will send a request to another service, which is API gateway. We can communicate with Lambda, with a Lambda function. So you'll probably hear of them. Lambda functions are cloud functions. In Firebase, there are cloud functions. In Google Cloud, there are cloud functions. In Azure, there are Azure functions, I think. But in the AWS, they are called Lambda because they like to rename things. So you connect via your WebSocket. Your WebSocket will call this Lambda, which is for executing just functions. This function will call DynamoDB, which is a serverless database from AWS, but you can connect to some other type of database. That database will hold a register of everyone who will be connecting to the server. So instead of a game server, so this seems more complicated. It's a little more complicated, but it's a good approach. We'll see why. So you can imagine you connect the WebSocket to some function, and that function stores who's connecting to the database. And then that database says, OK, John connected to the game. OK, I'll send it back to the other players. And you can see that the graphic is a little complicated, but basically it's the same as with web servers, but we add these middle layer services, which do the same thing. So it's basically using WebSockets, but it's cool that AWS added this feature that you can use WebSockets with serverless. Why use serverless? Because they scale easily. So you don't have to do anything. They scale quite quickly. You spend less time managing infrastructure. So you don't run your servers. It's like, OK, give me capacity for 10,000 requests per second. Good, you have to pay, but it's easy. You don't have to think about servers or anything. You'll probably first have to think about how to do all of this architecture that we quickly saw, but I don't want to spend that much time on that because you'll figure out. Just listen to these cool features. You can use it maybe in some non-critical real-time parts of the game, like the chat, or maybe some games that require real-time, but you don't need it to be like that fast. You can allow yourself some latency. And whenever the logic is not very complex, because you'll have to store it. So maybe if you have a game server, you can store a lot of logic in code, and it makes more sense that not having it on all the database and have to load it again whenever you have to do something. But the thing, and that's why I say non-critical real-time parts before, it's because the thing with these cloud functions is that they have cold starts, and cold starts means you make some request, you expect it to be spot on the moment so that you receive a response really quickly. But as you don't have servers, your code has to be somewhere. And what these cloud providers do is that sometimes they have some warm instance They usually do it with Docker or with their own platform services, and it's running there, but maybe it goes down because no one's using your application and they want to spend money. So whenever you make a request, the first request will take more time because it has to start up your application. So you also want to make your bootstrap time, your startup time really quickly. So maybe your first one won't be that quickly. And it also has some latency because, as you saw, you have to go through a lot of more services and a lot of more things, and each service adds more latency. So it's cool because it scales easily, and you don't have to worry about your infrastructure. But be careful with these two things because it can be like a game killer. Imagine you're playing Fortnite and you're trying to move like a head, and it takes 100 milliseconds to move one step. You're rage quit for sure. And I hope you know the guy on the bottom right now. I like him because it's also from Final Fantasy, but because his name is Cloud, and we're talking about Cloud, bad joke. Let's move on. Some other pattern that I wanted to discuss, and I don't like it that much, but we'll see it anyway. It's peer-to-peer games. You probably saw this approach in the past few years and maybe last year because it got really popular with WebRTC, which is a way of communicating with other people without the need of servers. So that's what peer-to-peer means. You have your computer, your phone, your device, and you're connected directly to some other computer, so you don't need a server. And the awesome thing about that is that you won't pay for servers. And what's better than free? Nothing. Well, but you have to pay some cost, and we'll see. So sometimes you need, and often you need some server because you need to know like the IP address of the other person, and you kind of like guess it. Maybe you can share it, but it's not like a great experience. And it's different from client-server architectures that we discussed before, and the one that you are usually using, because with client-server, you have your clients, your devices, they connect to the server, they get the response to the server, you send something, the server responds to you, and maybe they respond to other people. With peer-to-peer, you send it to everyone, and everyone has to send it to everyone. So imagine you are moving ahead, and you have to tell everyone, hey, I'm moving there. The thing is that when they respond, oh, it took some time for me to get your answer, but we'll see. So here, Mario and Peach seem to have a really good time, but we'll see. So peer-to-peer, players communicate with each other. So as we were saying, you have your device and it communicates directly with the other person's device. So it seems like it should be fast. You also save resources, so it's awesome. But in reality, it may be useful for games with very low amount of players because, as you saw on the previous graphic, you have to communicate all of your players with all of your players. So if you only have one player, it's awesome. You don't have to communicate with anyone, and isolation, and it's great. But if you want to be more social and in your game and you want to play with someone, you'll need a two-way communication. So you send your updates to someone and the other person sends theirs. And it's cool, works well. But what if you have like 100 players? Or what if you have 1,000 players playing on the same specific game? So from your computer, you have to send updates to another 1,000 players. And you cannot expect everyone to have such a great connection that can send it. So you can imagine that it will work better if you have less players. There are some approaches that you use a server in the middle and it can send some updates to others, but kind of defeats the purpose of having this peer-to-peer, at least in my opinion. So it also tends to be laggy. There's There's also some Mario game, like it's called Super Mario something Maker, Super Mario Maker 2, and it's made the multiplayer game of this game is made with peer-to-peer. And man, you have to see like all the people raging about how laggy it is. So slow. It could be such a great game, and it isn't. And it also can be difficult to control cheating because everyone's sending updates to everyone, and you'll have to have your game logic on your client side as well. So maybe if you're doing some of this Mario game, you'll need some server as well to control some stuff. But if you're playing with your friends, you can be cheating and maybe they won't even know. So peer-to-peer, wouldn't recommend it as a first approach, but maybe there's some good use case. And if you can make it work, you can save a lot of resources and money. So it's worth to give it a try, or at least to check it out. So we'll jump to the second part of the presentation. So this we have 3. This one will be much quicker, so don't worry, I won't bore you so much. But this is a really important part. So databases, you know them, but there are some differences with the ones you use, or you use the same ones, but you have to check out like what we do with in games. So this first quote, I took it from an AWS white paper about multiplayer games. So I trust them in this. So they probably have a lot more experience than me. And it's like the biggest bottleneck for online games tends to be the database performance. So it's not the server, which was surprising for me. And why is this? Because you have a lot of read and writes, and they will hit the database. And as you know, databases aren't as quick as servers in a lot of scenarios. So you'll have a lot of changes. And we were saying that you could have some stateful game server, so that you hold all the state there. But maybe sometimes you need these databases, or if we are using this PubSub model, you'll have to distribute some changes, and it can be like pretty challenging for your databases to be quick. So imagine you're using some relational databases. You'll find your boss like asks you to do some report, and maybe they take some time and they are slow, but it's okay. We run it once or twice, or you have to do some analytics. But with games, no, you have to do it quickly, everything. So we'll check like my first choice for games. There are some others, of course, but my first choice I would recommend is Redis for everything that you need to do for real time, because it's really, 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 really fast. So I should have added more really, because it's like a 1-digit milliseconds latency, and it also has some really cool data types like set, sorted set hashes. So you'll find that they are really useful when you are doing some leaderboards, or you have some counters. You want to have the number of players that are playing your game. You'll want to have different type of arrays, like holding different type of weapons, players, and you want it to be really fast. So as it is like a key store value, or you can use it mostly like that, you can retrieve your results really quickly. So it's also very useful for caching, like you use in your web applications, for sessions, as we said, for publisher subscriber models, and you can use it for your game features, as we were saying, leaderboards. Maybe you want to have a list of all your games, or maybe you have some inventory, maybe you have all you can think of, you have in a game that you want to store in some way. You can think of having it in Redis, and you want it to be stored like persisting in some database. So later you can send it to some processing. You can use it for some analytics. So first choice, go for Redis. And we see all our all-time favorites from like last century relational databases, SQL. And games, the games with SQL doesn't sound like that good, but in practice, you can use them. So whenever you have to do some transactions, you think of, you buy something and you want it to be secure. You want to have all of your purchases like on your database, and you want to know that they'll be there, you cannot lose them, and you want to do some awesome analytics and some awesome stuff you can think of. And maybe a SQL database will be a good choice. You can do advanced querying, so you can get anything you want. With Redis, you're limited because it has awesome data types, but it's not that flexible as you can as any SQL databases. You cannot do the same things. And you'll have this data persistence. You can have it in Redis as well, but it's more common to use this type of databases. People are very familiar with it, so you can use it as your primary database for anything you have to do. You want to sign up, you want to log in, you want to do like normal stuff, and you can allow yourself to make it not that quickly. Like it can be slow. Nobody will rage quit your application, your game, because it took 1 second to log in, to sign up. So it's perfectly fine for a lot of menu, parts of the game. You want to do a lot of stuff outside of the real-time game. So you can use SQL for this. You can do your app purchases, account records, and any transactional data. Or you can use some other database like non-relational databases like MongoDB, DynamoDB, Cassandra, or the one you like, the most modern one. And in some cases, they are faster than relational databases. You want to check like their transactional capabilities, but they have data persistence, so it's good. So no preferences on this. Maybe take a note on DynamoDB, which is AWS document solution for everything, because it's also really quick, and you can use it as with Mongo as a primary database to log all your user progress, achievements, friend lists, and everything you see on the menus. But you can use it also for caching your user sessions, and you can use it as a really quick data store like Redis. So definitely go and check it out. And then we see this one that it's pretty common in web applications. A lot of the time with front-end developers, they really like it. I like it as well, but we have a complicated relationship, let's say, because it has some limits. And whenever you're developing a very concurrent multiplayer game, things can get really difficult. So talking about that because of experience, but it saves us a lot of times, because when you're prototyping, when you're on your first iteration of your game, you can make things like really quickly. It has real-time updates, so you won't need any pub sub, so you can directly connect to Firestore, which is also a NoSQL database. And whenever you store something, let's say that you store, maybe not for a shooter, but maybe for a not so complicated game, like you're in a farm simulation, and let's say that you want to attack another person's farm. I don't know why, but I can imagine someone doing that. And you can send some notification, maybe these mobile games that are real time, but maybe you don't have to pay that much attention. So you can store your data, and maybe it's turn-based also, and it will distribute all of your real-time changes to the players that you want to be your changes distributed. So it's really cool. It auto-scales. You don't have to worry about servers, and it's easy to use. So you can also check it if you want to complicate yourself. And lastly, let's have a break, because I was talking too much about many things. So we'll see some design implementations. And I hope you're still enjoying the game. So in the meantime, you can tell me if which type of games you like, which game is your favorite if you haven't done so far. you have seen that I like a lot of Final Fantasy. So we'll see some design patterns. So in this case, a common design pattern, we discussed it before, it's leaderboards. So with leaderboards, you have two flavors of it. So one is global leaderboards, like these ones. You have your top players from all time, maybe from a monthly basis, from a weekly basis, and you'll have like them ranked by some points that you can calculate it the way you want, or you can have them like with this awesome game. Don't know if you know it. It's cool. It's the one that started IO Games, I think. But the thing you have to focus on is the one on the top right. So you'll see that there's a real-time leaderboard, and the approach you'll take with that is different than the other one. And we'll see why, because this one is real-time. So whenever a player like Germany there approaches "Don't eat me," I don't think anyone's gonna eat him. But whenever like one eats the other and it gains more points, so that will be reflected on the leaderboard. And you want it to be quick because you want to be like who's first, who's second. You don't want it to be like, okay, like 1 minute later or after the game finished, you know who was on first place. You want to have some real-time updates. So for real-time updates, you'll want to use Redis because we'll talk. We said that it has this awesome data type, so you can increment your score. You can decrement it. You can add more people. You can do a lot of stuff that's really useful for rankings and for leaderboards, and also check DynamoDB, as we were saying, because it's really quick and it also has some of these ranking capabilities. And yeah, then use API endpoints if you want to request like your global leaderboards, like the ones we saw previously. Do it as you would do with any usual database, but you can also use Redis for caching it. So let's say that you're requesting the top 100. They won't change it like that often, so you can use some cache over that. And you can update your leaderboards, like your global leaderboards, on a regular interval, like every 5 minutes, every 10 minutes, every 100 minutes, because you don't want to calculate everything every time a game ends. Imagine you're playing some multiplayer game, really popular, and you have to calculate all your leaderboards every time someone scores some new point or wins a game. It will be mad if you have like thousands and thousands of players, and imagine you start or you end the game like every 10 seconds. You'll be spending more time doing calculation on your database than you'll be doing displaying your results. They will change really often. So you can allow yourself that, and players are used to it. So as we were saying, you can also decouple that re-ranking process. You don't have to do it instantly whenever you finish a game. So if you have a game server that's processing your game, you don't need it to be like the one recalculating everything. You can put it in a queue. You can let a worker do that job, and you can do it, as we said, like in regular intervals. So do that, and use a stateful game server whenever you want these real-time updates, like we saw with Agar.io. And as we were saying, decoupling. So you want to decouple every part of your server that you can. So Ninja Fruit, there, bottom right. Is anyone playing it? I don't know. But again, sorry. Decoupling. So you want to decouple your application, your game, in a way that if you have a really, really, really slow process, like all of this recalculation of the leaderboards, you want to design your server so that it can operate independently. So you won't block your game server flow. You want your game server to be quick, to be awesome, to really rock. So in order to do that, you have to delegate. Like in life, you want to delegate some stuff that's boring, like calculating leaderboards. You want to be like the one doing the warrior stuff, like the shooting, the jumping, the adventure stuff. So focus on your game server on doing game logic and decouple everything that's not specifically related, like analytics, this processing of leaderboards or anything you can think that that's not directly related to the leaderboards, let someone else do it. So you can put some queues to do that, and you don't block anything. Some use cases, as we said, like you can calculate achievement, analytics, you can create avatar thumbnails. A really common scenario is that you have some worker that's creating some thumbnails for your image. So whenever you upload your awesome profile picture, the same server won't be the one that's resizing it and doing everything. Sometimes you put it on a queue, and whenever the worker says it has some time, so maybe it's from 9 to 5 because he wants to work from that time, but you can have it 24 hours. Robots won't complain. You can have it like create your thumbnails, and you can use these 3 services or anything, any queue service or message broker that you think it's good enough. You can use RavenQ, Apache Kafka, Amazon SQS. Any queue service, there's some good, cool implementations in the language you choose. For Node.js, there's one called Bull, and you'll find other cool implementations. And in the end, some of them use Redis, so it's also some good Redis use case. And we also talk about languages. Use the one that you think is best. As we said, in databases will be the most difficult part to scale here. So binary content. What I mean with this is basically using CDNs. So whenever the internet is down, it's usually because of this CDN service. I think like 2 weeks ago, the one on the bottom, Fastly, was down. And I went to Twitter, and instead of saying some emojis, I saw like some broken rectangles. It was funny. Well, for some people, it's not that funny, but okay, let's move on to binary content. So you're probably using this. So you can store your images, your avatars, your assets, your patches, your maps, everything you can think that's binary content in some storage server like S3 in AWS or any other server. And you can use a CDN to distribute it. A CDN is a content delivery network. So what that means is that you have a lot of servers that are in all over the world. So imagine you're the Czech Republic, you are in South America, you're in North America, you're in Asia. You have different servers that are caching your avatars, your images, whenever someone requests them. So whenever they request it again, they will be really, really quickly. So use them whenever you can. So you want to serve your assets really, really fast, and this is the way to go. And finally, we'll see a cool pattern for matchmaking, and this will be the end. So stay with me. We are almost there. And matchmaking is like one of the most common features in real-time games. So you basically choose a region, you select some game mode preferences, then the application makes some API requests, it finds some server, and then you connect to the server. But we'll see with a little more detail or with some graphics how it is done. And basically, you have all of these game servers. If you have a lot of money, and if your project is doing really good, you can have servers in all of these locations. By the way, some infrastructure providers like AWS have some awesome services like AWS Game Lift. So that makes spawning all of these servers in an easier way. Other cloud providers have their own way. So imagine you have all your Fortnite servers here in all of these parts. So why you want to have them everywhere? Because you want your players to connect near those locations. So with any big infrastructure provider, you'll find that you can spawn servers in a lot of places like these ones. But then you'll have your matchmaking servers. And why are they different? Because you want your real-time game servers to be just focused on your in-game stuff. You won't you don't want your game servers to be doing a lot of stuff. You want them to be focused so that you can track their performance, you can know what's going on, and then you can spawn these matchmaking servers, and maybe you have less of them, because while you're matchmaking, while you're like trying to find an opponent with a similar ranking like you know it takes some time. People are used to it. You don't expect it to be instant, because you'll think that you're probably matched with bots if it is too quick. So people are used to it, and you can have like a 1, 2, 3 different matchmaking services spawn in different places. And what you'll do is you'll connect to this matchmaking service, and these matchmaking services will recommend some different servers, game servers, depending on your location and depending on the location of the rest of the people are trying to join. So whenever, let's say, 100 people join the game, you're playing a battle royale and expecting like 100 players to join. So whenever they have like that capacity, they will request the matchmaking server. The matchmaking server will say, okay, so I'm really close to Czech Republic, but we'll have some other players that are in Spain, and we also have someone who's in the Netherlands. So maybe our best server is in Germany. So okay, we'll connect all to the server in Germany, despite maybe I have a server that's near my location. So you want to divide basically your type of servers, and you want to allocate some game servers, some matchmaking servers, and maybe you also have your API servers. I haven't put in them here, but you can distribute them like the matchmaking servers. You don't need them to be like extremely quick. You can allow yourself to have some latency. Why? Because all of this stuff costs some money. So whenever you can save it, it's good. And whenever you can respond to your players in a way that they expect. So for in-player game experience, really fast. And for the rest, okay. So it will save some money for you, and you'll have a really awesome game experience. So cool. The lesson is select your characters wisely. So that's servers, game servers, API servers, serverless, peer-to-peer if you want, your databases, your Redis, use whatever you want, but know all of the possibilities. There are more possibilities. This is like 101 of this stuff, but it's pretty awesome, and it's really fun to develop games. So give it a try. Choose wisely and have fun. So thank you, everyone. Game over. And that's how we finish the presentation. So, Michal, do we have some questions here?
Not yet. By the way, thank you for the presentation, Juan. We had one question asking about the game you actually work on, and I posted the links to a chat, so whoever didn't saw it, you can find it in the chat.
Awesome. So the game we're developing is called Life Penalty. You can see it in the link that Michal sent. So it's a game that features real goalkeepers, and we have 2 game modes, which are both live events, and we have pre-recorded events, not events, but goalkeepers. So what you want to do, if you like football, go check it out. You can choose with your player, with your application, where you want to shoot in a goal. So you have the whole goal, and you can choose wherever you want the ball to go. And if you make an awesome shot, you continue. You can win some cards of the goalkeepers. You can do some awesome stuff, and you. Oh, sorry. Yeah.
The important part which you really need to emphasize is that it's actually playing against real people, against the real goalkeepers.
Oh yeah, that's a good point. I'm not trying to sell the game. I'm trying to sell the multiplayer game part. So good to know. Yeah, you're playing against real people. It's a multiplayer experience. We were working with Firestore. We moved to Redis, and you can play with a real goalkeeper on a real stage, and a lot of people join that game and send their targets, and we calculate them in a very quick way. And we have our game servers there, so we'll do a lot of calculations, and we also do all of this API stuff that I was talking about for all the non-real-time game experience. And we also have live events, so every Wednesday or every 2 weeks, we have live events and people join, and there's a real goalkeeper there, which is awesome. We have a real machine that's shooting to that person. And then, like every day, like 24 hours per day, we have these goalkeepers recorded, so you can play against them. Unfortunately, some people think that we have goalkeepers there 24 hours a day because it feels really weird, really real. And some people complain, but it's not slavery. We let them sleep. So we recorded them, and you can play against them, but it's like a video on demand. So that's another awesome approach. So we're mixing really awesome, cool words like video on demand and gaming, which is something that I haven't seen, like just in ads, but not in a real game experience. So go check it out, and maybe we can have like some next presentation about it if you are interested. So cool.
Yeah, so no other questions. So I would say everything is clear. And I think we can wrap it up for today.
Awesome. Thank you everyone who stayed like for this long. I really appreciate it. And yeah, go and try to apply some of these concepts. I will be really happy to know what you're working on.
Yeah, okay. Thank you everyone.
Thank you. So if there are no other questions, I think that's it. Thank you everyone for your attendance, and thank you for Juan for a great talk. So if you want to join any of our future events, we will be hosting the next one in person finally, and it will be happening on June 13th, and we will be introducing our fastly growing department of data science. So if you don't want to miss that, check out our Eventbrite page or our website, and we promise you that we will be working on our next backend talks as well. So an important thing is that not even it's gonna be in person, but we will stream it online as well, so you can join it via Zoom or YouTube as you used to. So that's it from us, and since we want to be proud of everything we are doing, we would really appreciate your feedback. So I'm posting the link to the chat right now, and you should be able to see it also once you close your Zoom window. So please let us know what you have enjoyed, what you haven't enjoyed, or what are the another topics we should be focusing on. So that's it from me. Thank you very much. Enjoy the rest of your evening, and see you next time.